Good morning, ladies and gentlemen. My name is Martin Butterfield, and I'm one of the Application Development Managers for Hach in the UK. And I want to welcome you all to the fourth of our current series of webinars from Hach on wastewater applications. The presentation will last approximately 20 minutes, and as always with our webinars, we will keep questions until the end of the presentation, when we will answer them, and if need be, take them offline to discuss further. The way to ask a question is to type it into the panel on the left of your screen. This fourth presentation in our series is entitled Swing Zone Control for Activated Sludge Plants. It is presented by James Daly, another of our application development managers, and James has worked for us for the last 10 years and is highly experienced in our real-time control systems. Over to you now, James.
Thank you for the introduction, Martin. Good morning and welcome to our webinar on swing zone control of ASPs on a wastewater treatment plant. The aim of the presentation is to share some of the experience we have gained from working on sites within the UK and across Europe. This presentation itself will start with our description or definition of a swing zone. I will then cover how this can be of benefit, including the site-specific issues that the controller can help with. I will walk through the case study of the site that resulted in the development of the swing zone controller. Let's start by defining what we mean by swing zone. A swing zone is simply a way of dynamically extending the anoxic zone on an activated sludge plant. It uses the process information from the nitrification RTC to calculate where we can safely sacrifice a small portion of the aeration volume to drive higher denitrification performance. It does this by converting the first zone of a given lane from aerated to unaerated. Why would you want to do this? Why bother doing this? What are the benefits? So, increasing the anoxic volume has the potential to improve denitrification so much that it could result in a no-build solution. It can significantly reduce carbon dosing or remove the need for it at all altogether. Methanol has a health and safety implication and is very expensive. Other sources of carbon have their own issues too. It has the potential to improve settlement characteristics of the sludge. Using an anoxic selector zone is common practice in the UK to reduce the likelihood of filamentous bacteria dominating. So even when ASP plants don't have a total end consent, there is still a case to be made that swing zones could be applicable. Enhanced denitrification performance will lower the levels of nitrate in the final tanks. This reduces the possibility of nitrogen gassing off and potentially lifting the blankets. I appreciate this is less likely to be a problem where you already have a total end consent, but this can be an issue. Converting Zone 1 to unaerated will not only save on aeration energy, it will also make better use of the nitrate present in the return activated sludge, using the oxygen associated with that nitrate to provide carbonaceous treatment that would have otherwise required electricity. Increasing denitrification performance offers significant opportunity for alkalinity harvesting. In the UK, much lower phosphorus consents are on the horizon, requiring considerably more participant addition. In the future, alkalinity availability in the sewage is likely to be very important, and the swing zone controller can provide a level of denitrification for plants that were not originally designed to perform that task. Putting this another way, if you have a site with a new lower total end consent, the swing zone controller could help. If you have a site with sludge settlement problems, it may be possible to make a case for NRTC and swing zone. If you are concerned about the levels of alkalinity or the pH of your final effluent, then NRTC and swing zone could assist. Any site wanting to further reduce energy consumption will benefit from this system. In fact, if you have any sites with an NRTC, the swing zone can be a significant upgrade. Now, moving on to the case study that required the swing zone to be produced. The site was getting a new total N consent of 9.2 milligrams per litre. This was a large step change in treatment requirement, as previously it only needed to worry about COD and BOD. The site was very confined, with very little space to add further treatment. The water company wanted to avoid dosing carbon, as they already had sites using this method, and it's fair to say that they were not having too much fun running them. On this project, we worked together with the principal design engineers to ensure that the right control solution was offered and implemented. Luckily, we had worked on previous projects with both the solution providers and the client, so both were confident in our solutions. Due to the space restrictions on site, the maximum performance from the ASP had to be ensured. After modelling the new design, there was less headroom than normal asset standard designs, but still enough to work with. The foundation of the controls for our perspective are centred around the nitrification, or NRTC. This requires ammonia measurement at the inlet and outlet to allow feed-forward and feedback control. Ideally, sludge retention time is always included to maximise model accuracy, requiring solids measurement in the aeration basin and the RAS or SAS line, along with temperature, which we get from our dissolved oxygen probes. Determine ideal wastage rates, or more importantly, sludge age, to optimise biological conditions within the treatment basin. The ability to lift all the DO set points during times of high load really does improve the actual treatment capacity of any ASP, and was particularly important for this application. So here is a plan view of the original solution. It's a little confusing at first because the ASP is in an L shape due to the limitations of the available space, but it can be simply considered a 3-lane ASP with 4 aerated zones per lane. As you can see, there is a single ammonia measurement at the inlet, the little red circle at the top, nitrate measurements at the end of each anoxic zone used for the de-nitrification or internal recirculation RTC. A single ammonia measurement is used for the combined ASP outlet, the other red dot. Not shown are the solids measurements in the aeration basin and the RAS line for the sludge retention time RTC. This graph is to show how the plant performed when the RT was first activated. Just to be clear, this was without swing zone and it was pretty much out of the box performance before optimization. We had NRTC, sludge retention time RTC, and de-nitrification RTC for the internal recirculation. As you can see from the graph, the ammonia levels in the ASP effluent were low. The target set point was 0.5 milligrams per litre. And the nitrate levels at the end of the anoxic zone were very high, at levels peaking around 16 milligrams per litre. Of course, nitrate levels at the end of the ASP would be even higher due to the further nitrification of ammonia along the lanes. Poorly performing de-nitrification stage was the largest single factor to prevent consent compliance of the 9.2 milligram per litre total N. So a more detailed analysis was performed on the data to better understand what was the root cause of this process issue. It's worth mentioning here that online instrumentation was incredibly valuable in building this picture. A series of spot samples would have provided some information, but it would have been very labour intensive and taken a long time. Composite samples would not have been helpful, as further denitrification would have occurred in the sample reservoir, distorting the true picture. ASP influent ammonia, the highest marked point, the nitrate at the end of the anoxic zone, and the combined outlet ammonia at the end of the ASP were used to build the picture. This allowed process improvements to be made, which I will outline later. The net result of implementing all of these improvements is the following graph. So this graph showed the considerable improvement, with the nitrate levels peaking at around 6 milligrams per litre. This improvement was not enough to guarantee compliance with the limit of 9.2 milligrams per litre total N. This was just from other site-based improvements, and the RTC still running out of the box. To get to this point, the first improvement was to consider the performance of the aeration control. We studied and optimized the DO set points for each of the 4 aerated zones highlighted here. This included setting a maximum allowable DO level of 1.5 mg per litre in Zone 4, minimizing the DO returned in the recirculation line. Excuse me. We adjusted the set point factor to shift the ammonia treatment priority up the lane, allowing us to require less DO in Zone 4. A further improvement to the model was to account for hydraulic retention along the lanes. This ensured higher DO set points were only requested at times the higher ammonia load was in that zone. This is quite a nice graph that shows the improvements mentioned in the previous slide. The hydraulic compensation matches the ammonia load as it passes along the lanes. As you can see, the leading edge of Zone 1 occurs before Zone 2, etc. The maximum allowable DO in Zones 1 to 3 was 3 mg per litre, and in Zone 4 it was 1.5 mg per litre. This was reduced further at a later date. Both of these factors ensure minimum DO is returned back to the anoxic stage, minimizing inhibition of the denitrification rate. The next step was to focus on the internal recirculation itself. This simple process diagram shows how the DN-RTC uses a target nitrate set point at the anoxic outlet to increase or decrease the internal recirculation rate. So if the measured nitrate is below the target, it increases the internal recirculation flow and vice versa. This is how that looked on the site. You can just about see the return lines at the start of the anoxic zone. At the end of each, the internal recirculation is taken from near the end of the aerated Zone 4. The end of each, excuse me, the end of each anoxic zone had its own nitrate measurement for security, but a single nitrate measurement would have still worked. This is a nice slide showing the power of online information. You can see that the internal recirculation rate is at its minimum. The denitrification controller was working correctly as the nitrate levels were still above the target. When the nitrate levels approached the target of 2, you can see that the pumps kicked into life. The trouble was that the nitrate levels rarely dropped as low as the target level of 2 mg per litre. A full investigation into the poor nitrate removal performance identified that, given enough time, a fully nitrified effluent could be achieved. There was excess DO in the ASP feed. This was improved using RTC and flooding the PST ASP feed well to lower air entrainment. Sorry. The PST's performed so well at removing load, lower than ideal levels of carbon were present in the ASP feed. There was also high nitrate from a landfill leachate treatment plant in the catchment. One option was to implement a 4-stage BNR process with methanol addition. Extremely expensive option with undesired health and safety consideration associated with the methanol. Both delivery partner and the end user wanted to avoid this if at all possible. This simplified diagram is to simply show how the site conditions were giving rise to a very low recycle ratio and high total N. The high DO in the influent was inhibiting the denitrification rate and therefore the recycle rate. As mentioned previously, the RTC was prioritised to preferentially treat load further up the lanes in order to allow a lower maximum dissolved oxygen set point to be used in Zone 4, where the internal recirculation was taken from. The maximum DO in Zone 4 was lowered still further to 1.2 mg per litre. The primary tank desludge regime was changed to encourage more carbon load into the ASP feed. Additionally, sources of air introduced to the ASP feed were minimised by flooding the ASP feed chamber wet well, reducing the hydraulic drop that was entraining the air. Jar tests were performed to measure the expected performance for any given denitrification time. The results of that denitrification jar test showed that increasing the minimum denitrification time by 10 minutes would generate a 25% increase in nitrate removal performance. This gave us the confidence to proceed with providing the swing zones, as this would automatically generate a larger retention due to the increased anoxic volume. So it was agreed that a good approach would be to balance the priority between aerobic and anoxic volume. By converting aeration zone 1 to anoxic, the minimum retention time was expanded sufficiently to allow significant denitrification to take place, allowing the target set point to be met. Using both the dynamic internal recirculation flow and dynamic anoxic volume, even greater levels of ASP performance were achieved. In this case, the first steps to success were optimizing the recirculation rate through consideration of entrained air with both ASP feed and the DO's levels in the recycle flow. Just to re-emphasize, one of the many nice features of the NRTC is that you can apportion treatment within the lane by setting the set point factor in the parameterization page. This effectively allows you to shift the treatment further up the lane, giving a little more freedom to operate with lower DO values at the end of the lane, particularly helpful with internal recirculation. However, due to design constraints, these steps alone were not enough to get us past the finish line. It was by optimizing the anoxic volume that we provided a successful solution, adding the swing zone function. Understanding the real-time ammonia loading conditions allowed us to confidently sacrifice Zone 1 aeration. This is done in a stepwise fashion rather than selecting all lanes simultaneously. Blocking time is also employed to prevent unwanted frequent switches in aeration state. On top of that, consideration is also given to the number of times the zone has been switched, so the controller actively seeks to even out the number of times the swing zone is used across all lanes. In this application, we also had an option within the PLC for pulsed aeration, should there be any concerns over settlement, although the mixing in the anoxic zone was good enough not to require this. So this was the happy graph we had after all of the process modifications and adding the swing zone. The internal recirculation flow was now operating at maximum, with the nitrate target set point 2 mg per litre being outperformed. Operating with nitrate below 2 mg per litre provided very robust consent compliance and saved energy. The RTC at this site really did make a huge difference, and what was tailor-made for a specific need on this site is now available on our standard platform. I think it's fair to say that this plant could not meet consent without our advanced control. Not touched on here is the added protection given using the Sludge age controller. That controller allowed the site to never exceed the mass flux of the final tanks. There's no room to expand on that now, but feel free to view a previous webinar given by Stuart Ainsworth, either through our website or on YouTube. It is in leveraging the power of the NRTC that allows the swing zone function to perform so well. By understanding the loading conditions, this approach can really maximise the denitrification potential of any site. That's the story of how the swing zone came about. I think the key takeaways are: if you have any sites that are having difficulty meeting their existing total N limit or receiving a new lower total N consent, then we have a solution that can help. If you have any sites that are having difficulty meeting their existing total N, if you have a site that has sludge settlement problems, we can safely introduce or extend a selector zone using our swing zone. If the site has alkalinity concerns, we can harvest more alkalinity using the swing zone function. Even greater energy savings can be achieved with a simple add-on controller to the NRTC. Lastly, I would like to say this function will provide benefits for all existing NRTCs. Thank you very much for your time, and I'll be happy to answer any questions you may have.
Thank you, James. Right, yes, we have a couple of questions come in, but please, if you have some others, please do type them into your window, and we will we'll answer them if we can. Now, the first question, James, that's come through is, can a swing zone controller alone be incorporated into a plant that does not have real-time control?
No, the swing zone controller cannot be operated on its own. As I said in the slides, you need to have the NRTC on site as well to allow for the functionality to be used.
Okay, I have a second question here as well. Is there any risk to compliance when using swing zone control when it's activated?
No, there's no risk to compliance unless you actually lose the capacity to nitrify. If the ammonia set point is not being met with the NRTC, then the swing zone will be deactivated and it will return to an aeration state, and you should still be compliant.
Thank you for that, James. I've got another question come through now. Just look at it. For how long did the bench test on ASP1 take?
Not entirely sure what you mean. If you mean how long did it take to fully optimise the site, this was done over a number of weeks or months. It was quite a long time. It was a number of years ago. I can't remember exactly how long it took. I can try and find out for you, and I'll get back to you with that answer.
Okay, thank you for that. Now, I don't see any more questions coming through. So I'll just do the finish part, and if any more have come through, then we'll go back to questions. But anyway, thank you, James, for that. And thanks to everyone for the questions and attending the webinar. I would like to remind you all of the next webinar in our series. It will be on the control of DAF plants, and it's to be held on Tuesday, October the 17th at 10. And the next time I will be the presenter, so James can have a rest. Finally, we record all our webinars, so you'll be able to watch this and all of the others on the Hach YouTube channel. As we're nearing the end of 2017 series of webinars, please let us know of any subjects you would like us to cover in the 2018 series. Right, I've actually seen a couple more questions come through, so I'll just jump back to those now. Okay. Does the concept work if you have a combined activated sludge, nitrogen removal and chemical precipitation with ferric chloride?
I don't see any issues with the site working with nitrogen removal and chemical precipitation. We would obviously like to carry out a site visit to assess your site to make sure it would work, but I don't see any problems with that, no.
Okay, I have a few now. Have you specified? Sorry, yeah. Have you specified the NO2 emission and compared it to the process without the swing zone process?
No, I don't think we have. I'll have to check on that for you, and come back to you on that one.
But that would be the nitrite would be taken into account as a total N anyway, wouldn't it?
Yes, it would. Yeah.
How was mixing in the anoxic and aerobic zones carried out?
The mixing in the planned anoxic zone was with paddle mixers, and in the aerobic zone we used aeration pulse. So it was FPDA, and there was a timer set to open the valve to a predetermined position for a predetermined time, just to give a pulse of air to mix all the mixed liquors.
Okay. And then the next one, what energy savings were achieved?
I'm not sure if we were actually given the power consumption from the site. We normally reckon to achieve somewhere between 10 and 25% on normal power consumption for the ASP plant when installing an NRTC. There was more concern about meeting compliance on this particular site than the amount of energy savings that would be achieved. We can try and check on that, and I will try and get back to you.
Does the RTC principle work if you have a combined AS and MBBR process?
I know we do have some MBBR processes that are planned with an ASP plant. So yes, it does work. We haven't actually looked at the swing zone controller for this, though. Yes, we can work with MBBR processes.
Okay, that seems to be all of the questions now, but if you do think of any others, then please email us and we'll be happy to help you on those. Just to reiterate, if you have any other subjects you would like us to cover in 2018, please send us a mail, and we'll obviously try and include those in next year's. So that brings us to the end of this webinar. Thank you all for attending, and we look forward to speaking to you soon. Thank you very much. Bye-bye.